Hey guys, back at you with day 36 here. We have some more related rate problems, and I'm going to ask two questions about the same setup here, with one really big important kind of difference in how this works. Okay, so first off, go ahead and pause the video and write this question in your notes. You're going to want the entire question in there to reference. Okay. So again, it says a 15-foot ladder is sliding down the side of a building. At the instant the top of the ladder is 12 feet above the ground, the base of the ladder is 9 feet from the building. The top of the ladder is sliding down at a rate of 2 feet per second. At what rate is the base of the ladder sliding away from the building at that instant? So obviously, the first time I read a problem like this, it's just initial confusion all around. So what I want to do here is I want to get a sketch of the scenario on what's going on here. The important thing to keep in mind here is this ladder leaning against a building is going to be forming a right triangle. But it's really important to see all of the triangles that we've dealt with and rectangles and circles. Every aspect has been a variable, okay? That is not going to be the case this time. So I'm going to get a kind of a sketch here of what's going on. And here's what that's going to look like. So here's my building. And here's the ground. And here is this ladder leaning against the building. Okay? And what's happening here is this ladder is sliding down. Okay? So I'm going to annotate in a different color here. I'm going to use yellow to show how this thing, right, the ladder is sliding down, not sliding up. So it's going to look something like this. It's important to keep a couple of things in mind. The first thing is that the tip of the ladder here is moving down. The base of the ladder is moving away from the wall. And again, what we have here is a right triangle. We can assume that the building is it's not the Leaning Tower of Pisa, it's at a right angle to the ground. Okay. So this triangle, right, as time progresses here, this triangle is going to be changing. However, I want you to think about the three sides of the triangle. Are all three sides going to be changing like we've seen before, right? Like those two trains problems, right? In the two trains problems, all three sides of the triangle will be changing. However, in this problem, the ladder itself is 15 feet. Okay? And the ladder is rigid, so it is not changing. So when we label this picture, it's going to be very, very important here that we label it very carefully. Now, what I don't want to do is put in all of the numbers. Okay? What I want to do is something that is going to be changing, I want to call a variable. So I'm going to name it with a letter. Something that is not changing, I want to give its number. So what aspect, right? The height, the base, or the hypotenuse. One of those three is not changing, and that would be the ladder. The ladder never changes its length. It's always a 15-foot ladder. It's solid, right? It's not growing or shrinking. It's staying 15 the whole time. Okay, it's really, really, really important to get this set up correctly at the beginning. I do not want to use L for ladder or anything like that. There should be no variable here. I just want to use 15 for that ladder. Okay. However, as this thing slides down, I can tell that that base is going to be changing over time, and that height is going to be changing over time. So I want to assign those variables for my initial picture here. Okay? I realize now when I wrote this problem, I should have given you 12 but not 9, right? Usually they wouldn't give you all 3 instantaneous lengths. They'd make you see that 9, 12, 15 is really a 3, 4, 5 triangle. But I guess I accidentally gave you either the 9 or the 12. I should have just given you one of the two, right? But we recognize that as a 3, 4, 5 triple, okay? But right now, I want to assign variables for that triangle. And I can use B and H, I can use X and Y. Whatever you use, just make sure you're consistent with that the whole time, okay? I'm going to call the bottom part X and the top part Y. Do not draw your picture with 15, 12, and 9. Do not draw it with X, Y, and Z, or A, B, and C. The variables should be letters. The things that are staying constant should be constant. Okay? So it should look like this, either X, Y, and 15, or B, H, and 15, or whatever you need. Okay? It's very, very important to see that right now. Okay, so after I have this picture where variables are variables, constants are constants, what I'm going to do now is make a column of what I know. Yeah, the first thing I know is that the ladder is 15, but I don't even want to write that into my know column. It's just in my picture there as a reminder that that's always going to be 15. Okay? Because I don't want to say 15 equals some letter when it's not a variable. Okay, so I don't include that. What I do know is the top of the ladder is 12 feet above the ground. So what letter then would be 12? And would it be the letter or would it be the derivative of the letter? Well, 12 feet is not a rate. 12 feet is an amount, right? It's the top of the ladder, how high it is off the ground. So that would be y. So I'm going to write y equals 12. And again, I could have refrained from giving you this, but we know then that the base of the ladder is 9 feet away from the building, right? Here's the base of the ladder down here. Here's the building. That distance is 9, so I'm going to say x equals 9. What I know now is the top of the ladder is sliding down at a rate of 2 feet per second. It's really important here to see that what is happening to y, that distance from the top of the ladder to the ground. Well, as this ladder is falling down, y is going to be getting smaller in my triangle. So it's really, really important that you see dy dt is not 2, dy dt is negative 2. Very, very important to see that dy dt is negative 2. Okay. And then it says, at what rate is the base of the ladder sliding away from the building? So I want to know the rate of change from the base of the ladder distance to the building. Okay, well that distance is x, but I need to know the rate of change of x. So my need will be dx dt. Now, I don't know what dx dt is yet. I'm going to have to solve that. But what is important to know here is whether or not dx dt will be a positive number or a negative number. Well, again, as this ladder is sliding down, that distance x will be getting bigger. Okay, whichever side I drew the ladder on, x is going to be getting bigger. Therefore, dx dt should be a positive number. Okay, next. I need an equation that relates everything here. And again, anytime we see a right triangle with sides, we should be thinking the Pythagorean theorem. And that's what we're going to do here. But when we write our equation, it's important to know that x is varying, y is varying, but 15 is not. So my equation should look like x squared plus y squared equals 15 squared. Do not introduce a variable for something that is not a variable, right? I don't want to say a squared plus b squared equals c squared because I don't even have a and b, okay? But I don't want to say x squared plus y squared equals L squared or Z squared, because that's not varying. So it shouldn't vary in our equation either. Okay? And we know x is 9 at this instant and y is 12 at this instant, but it's changing throughout the whole process. So we have to keep it as a letter. 15 is not changing, so it can stay as a number. Okay, so the next thing we need to do now is the derivative. So I'm going to go ahead and do the derivative. Derivative of x squared is 2x dx dt plus 2y dy dt equals, now come on now, please don't tell me 2 times 15, okay? 15 squared is a number, it's 225. The derivative of a constant is always 0. So this needs to be 0, not 30, okay? Derivative of a constant is always 0. Okay, now what I'm going to do, I don't have a 2 in every side of the equation, okay? But I can divide by 2 because 0 divided by 2 doesn't change it. But I'll leave it in there just to show you that it doesn't matter. So I'm going to go ahead and plug in and solve for my unknown. I'm going to have 2 times x is 9, times dx dt. That's my unknown, so it's going to stay dx dt. Plus 2 times 12 times dy dt. I know dy dt equals negative 2. All right, I'm just plugging in all of my no's over here. Equals 0. So solving this out, I get 18 dx dt minus 2 times 2 is 4. 4 times 12 is 48. Equals 0. I'm going to go ahead and add over that 48. And I'm going to divide by 18. I know both of those numbers are, what, divisible by 6? I get 8/3, and again, my unit would be, I've been using, x is going to be measured in feet per second. So again, the top of the ladder is sliding down at 2 feet per second. The base of the ladder is sliding away at 8/3, right? Which would be 2.6 repeating feet per second. So they're moving at different speeds at that point in time. Okay, and again, I should do a little analysis here. It makes sense that my dx dt is a positive number. If I would have gotten a negative number there, something is wrong, right? And I probably forgot to make dy dt negative. Okay, so that's part 1 of the question. Part 2 is, same scenario here, but I want to know at what rate the angle is changing between the ladder and the ground. So that's the second part of this question. Okay. So here's what I'm going to do. I'm going to copy this picture down so I don't have to keep scrolling up and down. I have 15, y, and x. Okay. Between the ladder and the ground is this angle down here. That angle will be changing, so I'm going to have to name it a variable. The variable we generally use is the variable theta for angles. Okay. And again, here's what I know. I know x equals 9. I know y equals 12. I know dx dt. I just solved that. Dx dt was 8/3. I know dy dt was negative 2. Okay, let me just make sure I copied those down right before I get too far. Yep, x is 9, y is 12. And what I need is the rate of change of the angle. So I need d theta dt. And I'm going to have to write an equation. Okay, so now we have to channel our inner 9th or 10th grade selves when we worked with trigonometry, right triangle trig, okay? Because I want to write an angle that involves theta and x or y or both of them, okay? Now if we remember SOHCAHTOA, SOHCAHTOA gives me 3 possible equations that I could write. I could do sine equals opposite over hypotenuse. I could do cosine equals adjacent over hypotenuse. Or I could do tangent equals opposite over adjacent. Now, you could pick any of the 3 and all 3 will work. But usually there are some ways to do this that will make this a little bit nicer. First thing, I would like to only use one variable rather than 2 variables. Tangent, opposite and adjacent, right? From theta. Here's my opposite, here's my adjacent, and this is my hypotenuse. I don't want to use tangent because that's going to use both the variable y and the variable x. It would say tan theta equals y over x. I would have to do a quotient rule to solve that. Now, you're certainly welcome to do that, but on a timed test, you might want to stay away from tangent in this particular scenario. I could use sine or cos. Now, sine is going to involve y in 15. Cos is going to involve x in 15. I'd rather use y because the numbers are a little bit nicer. 12 and -2 is nicer than 9 and 8/3. But again, either way you do it, it should come out correct. Okay? So what I'm going to do is I'm going to write my equation. I'm going to use sine theta equals. So I know sine of theta equals opposite over adjacent. So that's y over 15. Because that 15 is a constant, I don't have to use, I do not have to use the quotient rule. What I am going to do, though, before I start doing the derivative here, a lot of times people struggle with the derivative of y over 15, okay? Whereas if they thought of it as 1/15 y, they totally know it. So I'm going to rewrite this thing real quick. The sine theta equals 1 over 15 y. What I'm doing is I'm writing it in ax to the n form, just like when we learned derivatives way back in the day. Okay? It's going to be a much simpler derivative to do quickly. Okay, so now I have to do the derivative. What's the derivative of sine theta? Well, we know that. The derivative of sine theta is cos theta. But remember, I have to tack on my d theta dt. Just like I've tacked on dr dt and dv dt and dh dt and dx dt, all those things. Okay? So we know the derivative of sine theta is cos theta. By the way, if you chose cos theta for your equation, then your derivative would end up being negative sine theta. Okay? Just something to remember. What's then the derivative of 1/15 y? Well, that's just a nice linear equation. The derivative of 1/15 y is 1/15. Remember, I need to tack on my dy dt. Now I should be able to solve for d theta dt. But I got a little bit of an issue here. I need to know cosine theta, okay? Now is when we can solve cosine theta at that instant. Cosine theta is adjacent over hypotenuse. But at that instant, we know that x is equal to 9. So cosine theta will be 9 over 15. Okay. I couldn't plug in that 9 until I've already done my derivative. So what I get is 9/15 d theta dt equals 1/15. And again, I got this from just doing adjacent over hypotenuse, right? Which was, my adjacent was x, which was 9/15. That's where that came from. And I have to do 1/15 times dy dt. Well, I know dy dt is -2. So -2 times 1/15 is -2/15. And now to solve this problem, all I have to do is get d theta dt alone. I'm going to do that by multiplying by the reciprocal, 15/9. So it cancels both of those. And I have to do that over here, 15/9. Those two 15s are going to cancel, and I'm going to get d theta dt equals -2/9. Our unit here, we always measure radians in terms of, we always measure angles in terms of radians. So this would be radians per second. Now, does it make sense that d theta dt is a negative number? Well, it should, because that angle is going to be getting smaller over time. Okay, that's it for this video. We'll do some more practice in class tomorrow. Talk to you guys later. 2 trains, bye.